Hi everyone, welcome back. In this video, I'm going to introduce to you the number theory concepts. If you are wondering why am I talking about number theory, that too in a cryptography and network security lecture series, let me give you the answer. Number theory plays a key role in modern day cryptography. Most of the public key algorithms like RSA, Diffie-Hellman, elliptic curve cryptography rely heavily on number theory. Concepts such as prime numbers, modular arithmetic, discrete logarithms are crucial for essential computations, including encryption, digital signatures, key generation, and hash functions. Number theory is not just a theoretical concept, but is a powerful and practical tool for development and implementation of secure cryptographic systems in our increasingly digital world. People who are interested in cryptography, we can call them as cryptographers, just like you, should have a solid foundation of number theory concepts or the basics of number theory to design and analyze algorithms that are both secure and efficient. So let's get going. What is number theory? Itself says that the name itself is self-explanatory. Number theory is a branch of mathematics that deals with the properties and the relationships of numbers, that is, positive integers. Applications of number theory that allow the development of mathematical algorithms that can make information, that is data that we want to send from one point to another point, unintelligible to everyone except for the intended users. Now let us dig deeper into this. Let us talk about divisibility first, because in the next coming slides, we are going to talk more about GCD. This will give you an basic understanding. If A and B are integers with A not equal to 0, then A divides B if there exists an integer C such that B is equal to A into C. So this is a common understanding of divisibility. When A divides B, we say that A is a factor or divisor of B and B is a multiple of A. You have to understand this notation. This notation, A divided by B, denotes that A divides B. Now, if you want to get a understanding of this particular denotation, you can say that if you write like this is valid because 12 is divisible by 3, because 12 by 3 is equal to 4, which is an integer. Now, if A by B, then B by A is an integer. You can understand if I write like this, or it even like this, 5 by 10 is equal to 2, because 10 divided by 5 is equal to 2. Now, if it's not possible, let us say that 5 divided by 9, this is not an integer. So you cannot write like this, and you have to mention it like this. We write it this because it does not divide B. These are some basics about the divisibility. Now let me dig deep and let's come across the most important concept that we are going to cover here today is your GCD, greatest common divisor, or it is also well known as highest common factor, HCF. Here, a non-zero B is defined to be a divisor of A if A is equal to MB for some M where A, B, and M are integers. This you have to understand that B is called as a divisor of A if there exists A is equal to MB, where A, M, and B are all integers. Now, this is the notation that we usually use, GCD of A comma B. A and B are two numbers here. It is used to denote the greatest common divisor of A and B, which is the largest integer that divides both A and B. Now, that is what we call as GCD. GCD of A comma B is equal to max of K such that K divides A and K divides B. I already explained to you about this notation, isn't it? You have to find the number, the maximum number, which divides both the numbers A and B. That is what we call as GCD of these two numbers A and B. Now, if you take 8 and 16, isn't it? 8 and 16 is 8. How do you write it? There are many ways of calculating GCD or finding out the greatest common divisor. This is one easiest way because these two are relatively simple and easy numbers. What are the factors of 8? 1, 2, 4, 8. What are the factors of 16? 1, 2, 4, 8, 16, isn't it? Now, if you find out these two both, what is the common and the highest number? 8. So the GCD of 8 and 16 is 8. This is another example for you. GCD of 24 and 30. Once again, you write the factors here. Okay, this is 24, my mistake. This is 24 and this is 30. Okay, so 1, 2, 3, 4, 6, 8, 12, 24. Factors of 30 are 1, 2, 3, 4, 6, 10, 15, 30. Out of these both, once again, you search for the common most GCD. Out of this, you can find that the commonmost thing is 6. So the GCD of 24 and 30 is 6. You can find it here from these two values. From these two sets, you can find it out, isn't it? Two integers A and B are relatively prime if and only if their common positive integer factor is 1. That means if there is no other values in these two factors except for 1, we call those two numbers are relatively prime to each other. If you say, in other words, you can say that if GCD of A comma B is equal to 1, then A is relatively prime to B and vice versa. The example being 8 and 15 are relatively prime because the positive divisors of 8 are 1, 2, 4 and 8 and the positive divisors of 15 are 1, 3, 5 and 15. You can see the common integer in both the lists of 8 and 15 is only 1. So 8 and 15 are called to be relative primes. Okay. Now, as I told you, there are several methods of finding the greatest common divisor. The first method which I had just shown you here is intersection of sets. That means you write the divisors of each or the factors of each number as a set, and then you find out the common set. You pick up the maximum value in that set. The next one is prime factorization method, and the most important method that we are going to cover today is Euclid's division algorithm. Now let me show you, let me give you some simple examples of these two methods. First, prime factorization and intersection of sets method. This I already explained. To determine the greatest common divisor of two numbers, we identify the set of all divisors for each number and then find the intersection of these sets. The largest element within this intersection represents the greatest common divisor. What do you mean by this, sir? Let me take a simple example and explain. Now let us try GCD of 12 and 18. Now, if I write the factors of 12 here as 12 is equal to, let me write down 1, 2 is a factor, 3, 4, not 5, 6, and then 12. Okay. Similarly, let me write it down for 18 also. 1, 2, 3, 6 are 18, 4 is not there, 5 is not there, 6 is there, and 9 is there, and finally 18. So what are the common values in these two? So S12 and S18, what are the common values? 1, comma, 2, comma, 3, comma, 6. So if you pick up the common values and the largest element in this set is your GCD. So the GCD of 12 and 18 is 6. This is quite simple method and it works well if you are dealing with smaller integers, not large ones. Okay, then let me show you about the prime factorization method also. So to determine the greatest common divisor, GCD of two numbers, we factorize both numbers into their prime components. That means each number is divided into its prime components. The GCD is then calculated as the product of the common prime factors, each raised to the lowest power present in either factorization. Once again, I will explain it with a simple example. Now, let me start with these two numbers. Let me take that. Okay. Give me a second. So rather than, let me try the same method of finding out the GCD for 12 and 18 using prime factorization. So I'm writing down the two numbers here, 12 and 18. So let me first divide 12 into its prime factors. 12 can be written as 2 into 6. 6 is a composite number, so it has to be further divided down. And I can write it as 3 into 2 or 2 into 3. So 12 can be written as 2 into 2 into 3, which is 2 square into 3. Similarly, let me break down 18 also. 18 can be written as, tell me, 3 into 6, isn't it? Once again, 6 can be written as 2 into 3. These are all primes. So 18 can be written as 2 into 3 into 3, which is 2 into 3 square. Now, what are the common factors in both 2 and 3? And what he's saying is you have to find out the GCD or calculate the GCD as the product of the common prime factors, each raised to the lowest power present. That means, what is the lowest power present in these two for 2? 2. So, 2. What is the lowest power present for 3 and 3 square? 1. So, 3. The GCD is calculated as 2 into 3, that is equal to 6, which is the same answer that we got here, isn't it? Now let me try somewhat bigger numbers using prime factorization method. Let us try for GCD of 192 and 360. Okay. So if we are going to try for this, let me do this. First, I need to break them down into their prime factors first. Now let me try for 192 here. So 192 can be written as 2 and 96. Okay. So 96 once again can be written as 2 and 48. So 48 can be once again written as, come on, 6 and 8. And 6 can be written as 3 and 2. 8 can be written as 2 and 4. Once again, 4 can be written as 2 and 2. So you have broken down a number 192 into its corresponding multiples of corresponding prime numbers. So 192 can be written as, you can write down here, 2 into 2 into 3 into 2 into 2 into 2 into 2. So I am writing down 1, 2, 3, 4, 5, 6, 7, isn't it? So if you break it down, how many 2's are there? 1, 2, 3, 4, 5, 6. So 2 power 6 into 3. This is what I got from 192. Let me do the same thing for 360. Okay. So let me break it down for 360. Now 360 can be written as 2 into 180. So 180 can be written as 2 into 90. 90 can be written as 2 into 45. 45 can be written as 3 into 15. So 3 is a prime factor. 5 can be written as 3 into 5. So they now have broken down all of them into prime factors. Now 360 can be written as 2 into 2 into 2 into 3 into 3 into 5, which gives me 2 cube into 3 square into 5. What are the common prime factors in these two numbers? 2 and 3 only, isn't it? And I told you that you have to take the multiplication of the lowest power present in the common prime factors. So what is the lowest between 2 power 6 and 2 cube? Lowest. So the GCD of 192, 360 is 2 cube into, next 3 is common, here 3 is common. And what is the lowest power of 3 and 3 square? 3. So you take 2 cube into 3, which is nothing but 2 cube is 8. 8 into 3 gives me 24. So your GCD for these two numbers using prime factorization is 24. This is another method. This is also okay. But once again, if you're talking about numbers of the magnitude of thousands and 10,000s, this takes quite a bit of time. So these are two of the common methods which are used for calculating GCD. And sometimes we can just inspect the numbers and routinely say that maybe if they're prime or not, and they can also give the answer for the GCD. But as I said, cryptography algorithms, and when you're dealing with security, we don't deal with small numbers, we deal with very large numbers. Then if that is the case, we go for the third method of calculating the GCD, which we call as the Euclidean algorithm. The Euclidean algorithm, also called Euclid's algorithm, is an algorithm for finding the greatest common divisor of two numbers a and b. So if you are given two numbers, for these two numbers, this algorithm can be used to calculate and find out what is their GST. This algorithm has broad significance in cryptography because this makes finding the GCD of large numbers quite easy. So that is the case. That is the reason why Euclidean algorithm is rated very high in cryptography. Now this is the algorithm. Let me tell you, if I wanted to find out GCD of A comma B, two numbers, isn't it? If this is the case, you have to start. First, let me see if A is greater than B or not. If it is not, you simply swap A and B and you get back here. And then you divide A by B, calling the remainder R. If R is greater than 0, you replace A with B and replace B with R and continue this process till you get the remainder as 0. If the remainder is 0, then the value of B will be your GCD. Of course, to look at this, you might think, what's happening here? There are some sites or websites on the internet which we call the Euclidean algorithm as long division also. Let me show you with a simple example. This is quite easy and quite fast if you want to calculate the GCD of two large numbers. So the result of the above is the following system of equations to calculate GCD of A and B. Now, if you take all these things, it might be a little confusing and you might feel what is all this happening. But once I take a numerical example and explain, it becomes quite easy. And also you can then read these equations and in a much more manageable way. So there are two numbers here. Let me assume that this is A and this is B. Now, according to my algorithm, first I have to check whether A is greater than B or not. Here A is greater than B. So that's fine. Now let me start working these things and how this algorithm works. First thing I do is I have to write down, I have to divide 710 divided by 310. You can see divide A by B, calling the remainder R. So initially I have to write down that 710 is equal to, if you divide 710 by 310, you get the quotient as 2 into 310 plus what is the remainder that is left. This is 620. 710 minus 620 gives me 90. So this is my remainder. So Q1 is the quotient, which is 2. B is your second number, 310. And R1 is the remainder for the first. Now, what you are saying is, the remainder is not 0, isn't it? It is 90. It is greater than 0. So you replace A with B. Now for the second iteration, what you're going to do is you're going to take this 310. So 310 is equal to, you do this, you perform the same kind of operations again. What you do is in 90. So you divide 310, replace B with R. So 310 divided by 90. Your R becomes the B. So if you take it 3 into 90, which is 270, plus what is the remainder that is left here? 40. So this is R1, this is R2. Now once again I got the remainder as greater than 0 value. So once I have to repeat the same operation again, but now 90 becomes A and 40 becomes B. So 90 divided by 40. I write that 90 is equal to, this is written as 90 is equal to 40. Divided by 40, you get 2 quotient, 2 into 40, which is 80 plus 90. Once again, if you observe, this 10 is greater than 0 value. So you repeat the same process. Now for 40 is equal to, the quotient is 4 into 10. What is the remainder? 0. Now I got the remainder as 0. If you see here, this process continues till R is greater than 0 or not. If R is not greater than 0, you come out of this loop and it says that GCD is the final value of B. What is the final value of B here? What is the final value of B here? You can see that the final value of B is 10. So the GCD is now written as 10. This is a simple method. Here simply we are performing the division of the numbers in an iterative way. This will be your R1, you can see R1, R2, R3. This process should continue, should go on till what? Till you get the remainder as 0. Only then you will get the GCD. In some cases, you might get GCD as 1. As I told you, if it is 1, we call them as relatively prime with primes. Okay. So this is an example of calculating GCD of two numbers using the Euclidean algorithm. For our purpose, I brought some other examples to get it to have a better understanding. Now, hopefully you understood how these equations are generated from here. We can see that R1 is less than B, R2 is less than R. Every time the remainder comes less than the previous one. And finally, you get the 0. And once you get the 0, whatever value is here will become the GCD of those two numbers. These are the equations that correspond to our calculations. And this is the algorithm. Okay. Now, let me show you. I brought 3 examples for us so that, and I somehow brought some numbers also, some large numbers, to show you how easy it is to calculate the GCD for any given 2 numbers using this method. Let me start with this one. So GCD of 2740 and 1760. Now this becomes my A and this becomes my B, isn't it? So let me start. So first I have to divide 2740 by 1760. Let me start. 2740 is equal to, how can it be written? The quotient will be 1 into 1760 plus whatever is the remainder. So 2740 minus 1760. It comes to 980. So this is my remainder. This is my remainder. Now, as I told you, because I have a non-zero remainder, I have to continue this process. This becomes my A now. So 1760 is equal to, you have to divide 1760 by 980. Once again, what do you get? 1 quotient. 1 into 980 plus what is the remainder of dividing 1760 minus 980? You get 780 as the remainder. You have to continue the same process because you are getting a non-zero remainder here. The next thing what I do is I'll write 980 is equal to 1 into 780 plus 200. Once again, I got a non-zero remainder. So I keep continuing the process. I'll take 780 is equal to, so 200, if I divide 780 by 200, I get 3 as the quotient. 3 into 200, which is 600, plus the remainder as 180. Now I write down again. 200 is equal to, by divided by 180, 1 into 180 plus the remainder is 20. Isn't it? Now I have to write 180 by 20. So 180 is equal to, tell me, 9 into 20 and the remainder is 0. So now what will be my GCD here? The value which is left as B once the remainder comes as 0. So using this algorithm, what I can say is GCD of 2740 comma 1760 is 20. You can try the other methods also to verify your answer if you are interested. But this is the answer that we got from this particular, using this particular method, and I cross-verified it. This is the right answer. So let me take another example, a somewhat larger example. Now, once again, I am checking A and B. Now, if you are wondering, sir, if this is, if the for the 43,215 is here and 72,345 is here, what to do? Nothing. You just simply swap the numbers. Now this becomes my A and this becomes my B. So let me write it down. First, we have to divide these with these. 72,345 is equal to, you divide A by B. Once again, I am getting the quotient as 1 into 43,215 plus what is the remainder. I have done these calculations already. If I were you, I will take a little bit, I'll be a little bit cautious and I'll take my time to do these subtractions and multiplications carefully, because most of the students make silly mistakes here. This is the remainder that is left. Once again, as the remainder is non-zero, I continue my calculations. So next, this becomes my B. So 43,215 can be written as, once again, the quotient will be 1, because we are dividing it by 29,130 plus what is the remainder. So 43,215 minus 29,130. It gives me 14,085. Once again, a non-zero remainder. So I have to continue. So 29,130 can be written as, if you divide it by 14085, if you take 2, 2 5s are 10, 2 8s are 16, 170, 28,170 will be the answer. So the quotient will be 2 into 14085 plus what will be the remainder? The remainder will be 960. Once again, I got a non-zero remainder. I continue the process. 14,085 can be written as, you have to divide 14085 divided by 960. If you are having a calculator, what I would do is, I'll simply type in 14085 divided by 960. I'll get some random value and I'll see the closest value and I will multiply it, get the answer and subtract it from 14,095. That is what I usually do. Now, if you do the same calculations, what I do is, you get as 14 into 980 or 960 plus the remainder will be 645. If you are wondering how did I get this 14, you do this simple calculation. 14,085 divided by 960 on your calculator. You will get something like 14.7 something, 78 something you will get. Now, if this is the case, you ignore the integer part. You calculate these two, 14 into 960. You will get the answer. And the subtraction between these two will be your remainder. That's all. So once again, I got a non-zero remainder. So I have to write it down again. 960 can be written as, I have to write it down as 1 into 645 plus what is the difference between 645 and 960? It is 315. Once again, a non-zero remainder. So I can keep continuing the same process. 645 is equal to, divided by 315. 2 into 315 gives me 630, isn't it? So 2 into 315. 645 minus 630 is 15. Once again, a non-zero remainder. So 315 can be written as, in 15, if you divide it by 15, if you take it, yes, 21 into 15 plus 0, because 20 15s are 300, 21 15s are 315. Now you got the remainder as 0. So what is my GCD? The value that is left in the B. Now, if we take this GCD of 72,345 comma 43,215 is equal to 15. This is using this. This can be done in matter of just minutes. If you use any other method, it will take considerably long time for us to get this answer. I'll do one more example before I proceed on to our next important concept. Let me try GCD of 144 and 55. Once again, let me use the same concept A, B, and I will write 100 and, let me change the ink so that it will be more easy for us. So 144 can be written as N55. How do you write it? 255s are 110, isn't it? 2 into 55 plus 110 gives me 34. Done. So it's a non-zero remainder. So I have to write it down as 55 is equal to 1 into 34 plus the remainder is 21. Once again, I have to write it down as 34 is equal to 1 into 21 plus 13. Again, 21 is equal to 1 into 13 plus 8, which is my remainder, but still non-zero. So 13 is equal to 1 into 8 plus 5, once again a non-zero. So 8 is equal to 1 into 5 plus 3, still non-zero. And 5 is equal to 1 into 3 plus 2, still a non-zero. So 3 is equal to 1 into 2 plus 1, still a non-zero. So I have to take this value now. 2 is equal to 2 into 1 plus 0. Now I got a 0 remainder. Now what is the GCD? What is the value in B position here? It is 1. So the GCD of 144 comma 55 is equal to 1. This is how you calculate it. It is a repetitive kind of division and it's quite easy to do the examples in this particular manner. Okay. So hope You understood, and you can take any kind of problems, any two numbers, any large numbers also, and using this method it is quite easy to find out the GCD. Which brings me to our next concept, which we call it as extended Euclidean algorithm. Now here till now we are actually calculating the GCD for any given two numbers. This extended Euclidean algorithm not only calculates the greatest common divisor d, but also it gives you two additional integers x and y, which are going to satisfy the following equation, where ax plus by is equal to d, which is nothing but your GCD of a comma b. The extended Euclidean algorithm is a powerful tool in number theory with several key applications, including finding the modular inverses for cryptography, modular arithmetic, and computer algorithms. The standard Euclidean algorithm gives the greatest common divisor, but if we extend it, we can discover how to write the GCD as an integer linear combination of the two original numbers. In a sense, this is the equation that we are going to get by calculating the GCD and extending this algorithm. GCD of a comma b is usually less than both a and b. You have to understand that either one of the x or y will usually be a negative value. In the next video, we are going to we are going to use this extended Euclidean algorithm to find out the multiplicative inverses in modulo arithmetic. Let me take you a simple example and let us find out how this works. Given a is equal to 102 and b is equal to 38, find GCD a comma b and the values of x and y. Okay, now let us use the same Euclidean algorithm which we used before to find out the values first. So a is equal to 102, and let me write it down as this is my a, this is my b. So 102 is equal to 2 into 38, because once you divide by 38, 2 into 38 is 76. 76 plus the remainder gives me 26. Now this is a non-zero. I continue. 38 is equal to 1 into 26 plus how much? 12. Right. So once again, 26 is equal to 2 into 12, which is 24. The remainder will be 2. So 12 is equal to, how do we write it? 6 into 2 plus 0. Because the remainder is a 0 here, the value which is left here is 2, which gives me the GCD of both the numbers of 102 and 38 is 2. This is the standard Euclidean algorithm which we just discussed before. Now extending it and getting the GCD, or writing the GCD as a linear combination of these two values, which includes a and b, is finding out in this particular manner. Let me show you. What we are going to do is we are going to write the remainder in a format. Now here, using this step, what I'm going to get is 26 is the remainder. How did you get it? We got it in such a way that 102 minus 2 into 38, isn't it? 102 minus 2 into 38. What is 102? A. So I can write it down as A minus, what is 38b? So A minus 2b. This is what we are writing as 26. What is the remainder here? 12, isn't it? So 12 is equal to, how did I get 12? 38 minus 1 into 26. Now what is 38? B minus of 1 into, what is 26? A minus 2b, which equals b minus a plus 2b, which I will get as minus a plus 3b. So 12 is written as minus a plus 3b. What is the next remainder? 2. 2 is nothing but, how did I get 2? 26 minus 2 into 12, which equals, what is 26 here? A minus 2b. Minus 2 into, what is 12 here? I can write it down as a plus 3b. Now if you break down this calculation, a minus 2b plus 2a minus 6b. So what do I get? Which equals 3a minus 8b. That means 2. So the GCD is 2. So the GCD of 102, 38, which is equal to 2, which I have written as 3a minus 8b. 3 is your x value. So x is equal to 3 and y is equal to minus 8. This is how you got it. Okay. This is, let me try another example for us so that it will get a little bit more, you will get a little bit better understanding. Now, if you just want to test it, so let me do that here. Now, 3 into 102 minus 8 into 38. This is 306 minus 8 is 64, 3 is 24, 30. So 304, which is equal to 2. Now, let me take another example as I just told you. Let me show you. Here, you can find that A is equal to 198, right? And B is equal to 168. You have to find out the GCD of A, comma B and the values of X and Y. So let me write first. Let me write down in the same similar sense that we wrote down earlier. 198 is equal to, you have to divide 198 by 168, isn't it? So 1 into 168. What is the difference? For the remainder is 30. So 168 is equal to, if you divide it by 30, I think it goes, quotient will be 5 because 5 30s are 150. 30 plus 18. Similarly, 30 can be written as 1 into 18 plus 12. Similarly, 18 can be written as 1 into 12 plus 6. So 12 can be written as 2 into, 6 into 2, isn't it? 2, sorry, my mistake. So 12 can be written as 2 into 6 plus 0. Now the remainder is 0. What I got here is the GCD of 198 and 168 is equal to 6. Now to implement the Euclidean algorithm, once again I have to follow the same steps, isn't it? Now let me find out how to write the remainders here. Let me start with 30. So 30 remainder, how did I get it? I got it as 198 minus 168, which is equal to nothing but A minus B. What is the next remainder I got? 18. So 18 is equal to, how did I get 18? 168 minus 5 into 30. This is what I got. So if I implement, 168 is nothing but B minus 5 into what is 30? A minus B, which equals to B minus 5A plus 5B, which is nothing but minus 5A plus 6B, that is 18. So next I will get it, what I can write it is 12. So for 12, what, how did I get 12 here? 30 minus 1 into 18. What is 30? A minus B, which equals A minus B minus 1 into, what is 18? Minus 5A plus 6B. So A minus B plus 5A minus 6B, which equals to 6A minus 7B. What is my next remainder? 6. So for 6, what do you get is 6 is equal to, what did I get 6? 18 minus 1 into 12. What is 18? 18 is minus 5A plus 6B minus 1 into, what is 12? 6A minus 7b, which equals to minus 5a plus 6b minus 6a plus 7b, which is nothing but minus 11a plus 13b, which is nothing but 6. So I can write down as GCD of 198, 168 is equal to 6, which is a linear combination of minus 11a plus 13b, where the values of x is minus 11 and y is equal to 13. This is how you use the extended Euclidean algorithm to find out the combination of these values of the x and y, where the GCD can be written as a linear combination of the given two values. Where we are going to use this Euclidean algorithm and how it is useful for us in terms of cryptography, we will discuss it in the next lecture. So hopefully you have understood these concepts well, and there are many problems that are available on the internet which you can practice so that you get mastery over calculation of GCDs and also implementation of the extended Euclidean algorithm. So till then, take care and good luck.